Obtain the mesh file and also the full training movie by purchasing this product. In this project, the cooling of an IGBT heatsink is simulated. An insulated-gate bipolar transistor, or IGBT, is a 3-terminal power semiconductor device primarily used as an electronic switch. An IGBT generates significant heat and can be affected by excess thermal energy. Using air cooling or liquid cooling techniques, heat sinks, this excessive heat can be removed, which can lead to improved performances, thus enabling much higher power densities and more compact modules. In this project, the cooling of an IGBT heatsink is simulated. The heatsink is in contact with a heat source on one side and the air flows on the other side. The airflow is responsible for cooling the heatsink. Energy model is activated to analyze the heat transfer rate, and the Laminar viscous model is activated to solve the airflow. The geometry for analyzing this simulation consists of a heat source and a heatsink. The geometry is designed and meshed in Gambit. The mesh type used for this geometry is unstructured. The present simulation and its results are considered to be steady and do not change as a function of time. From the mesh display section, we can display all of the surfaces and boundaries included in the geometry. These are 3 different zones, including aluminum, fluid, and iron. As it can be seen in the boundary condition section, the heat source thermal condition is equal to the heat flux, and the heat flux magnitude has been identified in this section. As this wall has been placed between 2 different zones of fluid and aluminum, so the thermal condition of these kind of walls should be identified as coupled. And because these walls are coupled, a shadow condition will be made automatically, that all the boundary condition and thermal condition of these 2 walls, I mean wall aluminum fluid and wall aluminum fluid shadow, are completely as the same. All the other walls existing in this CFD simulation are stationary wall with no slip, and also thermal conditions of all the other walls are defined as the convection with heat transfer coefficient equal to 5 and also free stream temperature equal to 300 degrees of Kelvin. The simple algorithm in the solution methods section uses a relationship between velocity and pressure corrections to enforce mass conservation and to obtain the pressure field. Also, the pressure velocity coupling scheme controls the manner in which pressure and velocity are updated. When the pressure-based solver is used, the scheme can be either segregated, like simple, that pressure and velocity are updated separately, or coupled, that the pressure and velocity are updated simultaneously. ANSYS FLUENT provides the following segregated types of algorithms like simple, simple C, piezo, and fractional step or FSM. In general, segregated methods like simple that has been chosen in the CFD simulation are faster per iteration, while the couple algorithm usually requires fewer iterations to converge. Here is the 2-dimensional temperature contour and also the velocity contour. Suppose that we are going to obtain the Nusselt's number on every desired wall, or also we are going to obtain the temperature difference between the inlet and outlet boundary condition. We should select the surface integral from the report section and also area weighted average. Then we should identify the field variable. The applied settings are summarized in the following tables as a review. Obtain the mesh file and also the full training movie by purchasing this product. To benefit from Master CFD services including simulation, consultation and training, contact our experts via info@mastercfd.com or www.master-cfd.com.